Welcome to a screencast on an introduction to chemical equilibrium. Let's start by considering the reaction of nitrogen and hydrogen to make ammonia, NH3. And if we were to have some nitrogen and hydrogen, the reactants, in a container, and they were in a situation where they could react, we might expect to produce ammonia, NH3. Now, in reality, many chemical reactions don't go 100% to completion. So in this case, the reaction of nitrogen and hydrogen would not completely produce ammonia. It would produce some ammonia, but some nitrogen and hydrogen would be unreacted or still left. Now, if the container is sealed so no materials can get in or out, and it's kept at a constant temperature, then eventually we reach a situation known as chemical equilibrium, where reaction still continues on a microscopic level or submicroscopic atomic level, but the concentrations of the reacting species and the species that are being produced, those stay constant. Now, let's consider essentially the same reaction, but in reverse, ammonia, NH3, making its elements nitrogen and hydrogen. And essentially we could do the same thing in reverse. If we put some ammonia, NH3, in a container in a situation where it could react, it may react to make nitrogen and hydrogen. And conceivably it could go 100% to make nitrogen and hydrogen, but in reality, in most situations, it will do so partially. Some ammonia will be made, but some nitrogen and hydrogen will remain. And once again, if we have a closed container at constant temperature, we'll eventually reach chemical equilibrium. Now we can put these reactions together because essentially they're the same reaction but in opposite directions. And so rather than writing two reactions, we simply write one reaction but with two arrows. And the arrow to the right indicates that nitrogen and hydrogen can make ammonia. The arrow to the left indicates that ammonia can make nitrogen and hydrogen. And we often use this for situations of chemical equilibrium. And in this case, we can either start with nitrogen and hydrogen, or we can start with ammonia. And when we put those in a container and allow them to react, eventually they reach a position of chemical equilibrium where we have some ammonia produced or some ammonia left from what we started with, some nitrogen and hydrogen produced or some nitrogen and hydrogen left from what we started with. And what characterizes this chemical equilibrium is that the concentrations of the reactants and the products are all constant. So when chemical equilibrium is reached, the concentration of nitrogen will be constant, the concentration of hydrogen will be constant, and the concentration of ammonia will be constant. Now we can look at graphically what occurs if we were to, let's say, start with no ammonia in our container, and we put in maybe an initial concentration of 1 molar nitrogen and 3 molar hydrogen. And if all we have are nitrogen and hydrogen, the substances on the left-hand side of this chemical reaction, the only thing they can possibly do is make ammonia. So the concentration of nitrogen will decrease, and the concentration of hydrogen will decrease. And note that for every 1 nitrogen that reacts, 3 hydrogens react. So the concentration of hydrogen will go down 3 times as quickly as the concentration of nitrogen goes down. And starting with 0, the concentration of ammonia goes up because ammonia is being formed, and it has its concentration increase twice as fast as nitrogen and 2/3 as fast as hydrogen. And then note, if we wait long enough and we have a sealed container and keep the temperature constant, eventually we reach a situation where the ammonia concentration is constant, the hydrogen concentration is constant, and the nitrogen concentration is also constant. Now, if we started with different initial concentrations of hydrogen, nitrogen, and ammonia, for example, we could start with them all having the same concentration. And depending on the circumstances, nitrogen and hydrogen may be produced, as they are in this case, and ammonia is used up, as it is in this case. Or we could start with concentrations such that the reverse occurs. But in either case, eventually we get to constant concentration of each substance that's involved. So if we do some experiments with this system of nitrogen, hydrogen, and ammonia at 450 degrees Celsius, we find the following. We can have an initial concentration of nitrogen, hydrogen, and ammonia as indicated, 0.500 molar for each of them. And when we reach equilibrium, we find the following concentrations of the substances at equilibrium. And then we do a different experiment with different starting concentrations, and we get the following equilibrium concentrations. And then we do it again, and one more time. So each time we start with different starting concentrations of the substances involved, and each time we end up with different concentrations of the substances at equilibrium. And if you look at these numbers, there's nothing super apparent in terms of any kind of consistency or obvious generalization. But if you spend a little bit of time looking at the numbers and trying various possibilities, what you find is the following. If we make a ratio of the concentration of ammonia squared at equilibrium over the concentration of nitrogen times hydrogen cubed at equilibrium, we find the following. We get 0.153 for experiment 1, 0.152 for experiment 2, 0.152 for experiment 3, and 0.154 for experiment 4. Now, these numbers are essentially the same value, certainly within experimental uncertainty, and so we have a constant value for our various starting concentrations of substances, and this is what's known as an equilibrium constant. And in general, what we find is every reaction is going to have an equilibrium constant, a constant value regardless of what you start with for your initial concentrations of substances. And interestingly enough, if you look at this, you'll note that the exponent for the ammonia is the same as its coefficient, as is the case for nitrogen and hydrogen. The exponent and coefficient for each substance are the same. And this turns out to be true in general, but specifically, first of all, for the reaction making ammonia from N2 and H2, what we find is that K sub C, this is what we use K to symbolize our what's called equilibrium constant, and it has a subscript C to stand for concentration because we're using concentrations of substances. It turns out that that ratio is a constant value for a given reaction at a given temperature. And it's a ratio of what we've typically been calling products, but now we're going to just call the substances on the right-hand side of the equation over the quote-unquote reactants or substances on the left-hand side of the equation, and they're going to be raised to the power that corresponds to the coefficient of that substance in the reaction. And for a general reaction, a generic reaction, A and B being reactants and C and D being products, and M and N being the coefficients of the reactants and X and Y being the coefficients of the products, what we find is that the equilibrium constant expression is K equals, and if we're doing concentrations, K sub C, concentration of one product to its coefficient as a power, second multiplied by second product times its coefficient as an exponent, and if there were more products, we'd continue that process. And then for the reactants, same idea, but they are in the denominator. And we should note, if we're dealing with gases, we often do equilibrium constants in terms of pressures rather than concentrations. And then we'd have a case of P, or a pressure equilibrium constant. And the format is the same, but we use pressures rather than concentrations in molarity. Now, a couple other things to note. The equilibrium constant is specific for a given reaction. It depends on how you write the reaction, and it depends upon the temperature at which the reaction is or takes place. And if we have an equilibrium system with some pure liquids or pure solids in the system, then we don't include the pure solids or liquids in the equilibrium constant expression. This is a convention we use, and it's because pure liquids and pure solids have constant concentration, so their concentrations aren't changing, and so we leave them out of the equilibrium constant expression. Okay, so let's take a look at an equilibrium calculation problem. And this one, we have a flask with hydrogen and bromine, each initially at a concentration of 0.50 molar at 700 Kelvin. And at equilibrium, at the same temperature, the concentration of HBr is 0.80 molar. So the question is to calculate K sub C for the reaction below. And how we typically do equilibrium calculations is we set up a table starting with our initial concentrations. And in this case, we have an initial concentration of 0.50 molar for H2, 0.50 molar for Br2, and we initially don't have any HBr. No concentration was given for that because there isn't any initially. Now, the H2Br2 and HBr concentrations will all change as reaction proceeds until equilibrium is reached. And we don't actually know what the change is yet, but we do know HBr must be produced by this reaction. The reaction must go, quote unquote, to the right, because we start with no HBr, so the only thing it can do is be formed. And therefore, H2 and Br2 must be used up, they must react, and so the concentrations of H2 and Br2 will decrease, and the concentration of HBr will go up. Now, even though we don't know what the concentration changes are exactly, we can relate them to each other by using X to symbolize unknown change, and then noting that the H2 concentration goes down. The Br2 concentration also goes down, so we have a negative sign indicating decrease in concentration. And then the HBr concentration increases, and we put a factor of 2 in front of the X for HBr, because for every 1 H2, it reacts with 1 Br2 and produces 2 HBr. So the stoichiometry indicates a 1 to 1 to 2 stoichiometric relationship for the changes that occur. Now, if we know the initial and the change, we can get the concentrations at equilibrium. In this case, they're going to be in terms of X. We start with 0.50 molar H2. It goes down by X. So at equilibrium, we have 0.50 minus X. Br2 is the same thing. And HBr starts at 0, goes up by 2x. So it's 2x at equilibrium. Now note, the problem tells us that at equilibrium, the flask contains 0.80 molar HBr. So 2x is actually equal to 0.80 molar. Well, if 2x is 0.80 molar, then x must be 0.40 molar. And what this does is not only do we now have the concentration of HBr at equilibrium, but we can figure out the concentrations of H2 and Br2 at equilibrium. So HBr is 0.80 molar, and H2 is 0.50 minus X, which is 0.40, so H2 is 0.10 molar at equilibrium. Br2 is exactly the same thing. 0.50 minus 0.40 is 0.10. And so we now know the concentrations of each substance at equilibrium. And if we remember that the equilibrium constant expression, K sub C, is HBr squared, so the products or the substances on the right raised that concentration raised to the raised to the coefficient, in this case 2, and then divided by the product of the reactants or the substances on the left, and those are H2 as well as Br2, and each is to the first power because their coefficients are 1. So now it's just plug in values. 0.80 is HBr, and we square it. H2 is 0.10, Br2 is 0.10, and we do the calculation and find an equilibrium constant value of 64, and this is for the reaction above at 700 Kelvin. So we would say K sub C is 64 for the H2 plus Br2 makes 2HBr reaction at 700 Kelvin. Now, the second problem is the dissociation of hydrogen sulfide into its elements, hydrogen and sulfur, when it's heated. And we are now dealing with pressures. We have a known initial pressure of H2S, and we are to determine the partial pressures of H2S, H2, and S2, all of the species involved in the equilibrium, at 1132 degrees Celsius. And note, we, in this case, are given an equilibrium constant value. K sub P is 0.0026 at the temperature we are dealing with. And as before, what we do is we set up our initial change in equilibrium, or what's sometimes called an ice table. And our initial pressure is 0.100 atmosphere for H2S, and we have no hydrogen or sulfur to begin with. Now, since we have some H2S and no H2 and no S2 initially, we know the reaction has to go to the right, making H2 and S2 and using up H2S. And we don't know how much it's going to react, how much change there will be, so we're going to symbolize that by X. And what we do know is if S2 changes by some amount, we'll call it X, and we know this is positive because S2 is being formed, then we know H2 is going to change by twice as much because it's 2-to-1 stoichiometry. And then we know that H2S will also be 2 times as much, but it's going to have a negative sign in front of it because its pressure is going to decrease as that substance reacts. Well, at equilibrium, so our next row is the equilibrium row, we're going to have 0 plus x is, of course, x, 0 plus 2x is 2x, and 0.1 minus 2x is 0.1 minus 2x. So those are the pressures of the respective substances or species when equilibrium is reached, and all of those are in terms of x. Now, how do we solve for x? Well, remember that we know the equilibrium constant expression. K sub P is the pressures of the products or substances on the right-hand side raised to the appropriate exponents, divided by the pressures of the reactants or the substances on the left-hand side raised to their appropriate exponents. So K sub P is pressure of H2 squared times pressure of S2 over pressure of H2S. And we'll now sort of tote up our where we got to in the last step. We knew the equilibrium pressures in terms of x. We know the form of the equilibrium constant K sub P, and that is in terms of pressures of each species. So we can substitute in our expressions in terms of x for the pressures into the equilibrium constant expression, and we get the following. Pressure of H2 is 2x, and that gets squared. Pressure of S2 is x, and that's to the first power. Pressure of H2S is 0.100 minus 2x, and that gets squared. And then remember that this equilibrium constant actually has a value. It's 0.0026. So what we have is an expression in terms of only one variable, x, that is solvable. Now, we'll talk more about how to solve these types of more complicated equations, but for now we're just going to say, okay, we do the math and we solve it, and we get our answer. In this case, it's x equals 0.015. Well, now that we know what x is, what the change is, we can determine what the pressures of each of these substances are at equilibrium. So S2 at equilibrium is equal to x. X is equal to 0.015. So the pressure of S2 at equilibrium is 0.015 atmospheres. 2x is the amount of pressure of H2 at equilibrium. So that's 2 times 0.015 or 0.030 atmospheres for H2 pressure. And then H2S is 0.1 minus 2x. And again, x is 0.015, so it's 0.1 minus 0.03, which is 0.07. So the pressure of H2S at equilibrium is 0.070 atmospheres. And then one last thing, it's often a good idea, if you have time, to do a quick check to make sure you solved things right. And if you did everything right, then the pressure of H2 squared times the pressure of S2 divided by the pressure of H2S at equilibrium, when we do that ratio with these values, we should get about 0.0026. Might vary just a little bit because of some round off types of uncertainty, but we should get about that value. And if we do that calculation, we check and we do in fact get the K sub P, and we know we did the math right and solved the problem correctly. And that's it for Introduction to Chemical Equilibrium screencast.